Hey everyone, Mr. Houck here. In today's video, we're going to be looking at Unit 6, the Trig Identity section of the Semester 2 Final Exam Review for Pre-Calculus. Let's go and get started. So number 11, our first problem here in the Trig section, says to use the sum and difference formulas to solve the cosine of negative 19 pi over 12. So what we're trying to do here is you're going to notice that negative 19 pi over 12, you're not going to find that anywhere on our unit circle. So we need to find a combination of angles, either through addition or subtraction, of angles that are on the unit circle to give us negative 19 pi over 12. And notice that the angles that I think will work best, or at least just the ones we used in this example, are pi over 6 minus 7 pi over 4. And if we look at the unit circle, pi over 6 we know is the same as 2 pi over 12. 7 pi over 4 is the same as 21 pi over 12, and we're converting them into with a common denominator of 12, just so, again, so they have common denominators, and it's easy to make those calculations. So we can see that if we do 2 pi over 12 minus 21 pi over 12, you get negative 19 pi over 12. So we're going to use pi over 6 and 7 pi over 4. All right, so now we have a cosine subtraction problem. And the formula, the difference formula for cosine is cosine alpha times cosine beta plus sine alpha times sine beta. That's our cosine subtraction formula. So that's what we do here, and we're going to let pi over 6 be alpha, we're going to let 7 pi over 4 be beta. So we just plug in the pieces where they go, okay? So this is what we get. Now we need to evaluate each one of these using the unit circle. So the cosine of pi over 6, if I jump over to the unit circle here, well, here's the angle pi over 6. Cosine is the x value, square root of 3 over 2. Cosine of 7 pi over 4, so we want the x value at 7 pi over 4. That's going to be square root of 2 over 2. Sine of pi over 6, so sine, we want the y value at pi over 6. So here's pi over 6, there's the y value, 1/2. And sine of 7 pi over 4, we want the y value at 7 pi over 4. Well, here's 7 pi over 4, there's the y value, negative square root of 2 over 2. And now it's just an algebra calculation. So square root of 3 over 2 times square root of 2 over 2, when you multiply square roots, you multiply the numbers underneath the square roots and you keep the square root there. So root 3 times root 2, that's root 6. And of course, in the denominators, we multiply those together. 2 times 2 gives us 4. Over here, 1 times negative square root of 2 in the numerator, just get negative square root of 2. Then of course, 2 times 2, we get 4. This would be an acceptable answer. Or, since they both have the same denominator of 4, we can just combine the numerators together and get square root of 6 minus square root of 2 over 4. All right, number 12 is a verification problem. Recall for trig verification, you're trying to make one side of the equation equal to the other side of the equation. And we typically don't work on both sides at the same time. Usually, in the majority of cases, it's the left side of the equation that you're going to work with. So I'm gonna take tangent of x plus cotangent of x squared, and I'm gonna mess with this until I get it to equal secant squared plus cosecant squared. So tangent x plus cotangent squared, that's gonna be tangent x plus cotangent x times itself, tangent x plus cotangent x, which means I'm gonna FOIL. So foiling, first times first, tangent times tangent is tangent squared. Outside times outside, tangent x times cotangent x, which is just tangent x times cotangent x. Insides, you're going to get tangent x times cotangent x again, and then last terms, cotangent x times cotangent x, you're going to get cotangent squared x. Next, notice that I'm saying that tangent times cotangent is just 1, and that's because tangent and cotangent are reciprocals of each other. Another way to really easily see this is if you take tangent and cotangent and convert them into sines and cosines, we know tangent x is sine x over cosine x. If I multiply that by cotangent, which is cosine x over sine x, we can see all the canceling happening that just results in a 1. Okay, so tangent times cotangent is just 1, and we have 2 of those. So now we have tangent squared plus 1 plus cotangent squared plus 1. And if you look at your trig identities, if you look at the Pythagorean identities, tangent squared plus 1 is secant squared, and 1 plus cotangent squared is cosecant squared. Those are right down here. Tangent squared plus 1, secant squared, cotangent squared plus 1, cosecant squared. But that's exactly what we wanted to prove in the first place. So we are done, end of proof, end of our verification, and we can move on. All right, number 13. This one is actually pretty tough. This is a trig simplifying problem, and there's a lot going on here. So if we look at our initial problem, we want to simplify 2 over 1 plus cosine x minus 1 plus cosine x divided by 1 minus cosine x. Here we're going to have to get a common denominator. So I'm going to multiply 2 over 1 plus cosine x times the other denominator, 1 minus cosine x, top and bottom. And I'm going to multiply 1 plus cosine x over 1 minus cosine x times the other denominator, 1 plus cosine x, top and bottom. Over here on the left, just distribute the 2. 2 times 1, 2 times negative 2 cosine x. You get this piece. Over here, these are going to need to be FOILed. So 1 times 1, there's 1. 1 times cosine x, and then 1 times cosine x again is going to give you 2 cosine x. So that's combining the outsides and the inside pieces. And then last times last, cosine times cosine gives us the cosine squared. Notice that we have this subtraction sign in the middle. So this entire thing that we FOILed is being subtracted. You don't want to forget that. You don't want to mess up signs because you're forgetting to apply the subtraction sign. All right. In the denominator, common denominator, let's go ahead and FOIL it. So again, 1 times 1, there's 1. 1 times cosine, there's cosine. Negative cosine times 1, there's negative cosine. Negative cosine times cosine, there's negative cosine squared. Now we start to simplify this thing. So I went ahead and took this minus sign, distributed it as if it was a negative 1. That gets us these pieces. They just change signs. And in the denominator, cosine and negative cosine cancel each other. So all we have left is 1 minus cosine squared. Okay. Next, in the numerator, let's start simplifying some stuff. 2 minus 1, those are like terms. That'll just be a positive 1. Negative 2 cosine, that's negative 4 cosine. Negative cosine squared doesn't have any like terms. It's going to stay the same. I also do some rearranging here. So this 2 minus 1, that's going to give us a 1. 1 minus cosine squared, I group together because I already know that that's going to give sine squared because of a Pythagorean identity. So that's just something to keep in mind there. So here's how I got everything rearranged. 1 minus cosine squared minus 4 cosine x. I have this 1 minus cosine squared in top and bottom. Pythagorean identity, 1 minus cosine squared is sine squared. So I replace both of these with sine squareds. And now what I'm going to do is I'm going to split the fraction. I'm going to go sine squared over sine squared minus 4 cosine over sine squared. And we can see that sine squared over sine squared is just 1. The minus 4 cosine over sine squared, I go ahead and break up into 4 times cosine over sine times 1 over sine. The cosine over sine will give me cotangent. The 1 over sine will give me cosecant. And I really can't get any more simplified than that. So that's going to be the end of our problem. All right, number 14, a double angle problem. Find tangent of 2 theta, given that the sine of theta is 4/9 and that theta is between pi over 2 and pi. So with these kinds of problems, we needed to use these domain restrictions to set up triangles in the quadrant. Now, pi over 2 to pi, this is quadrant 2. Okay? Because pi over 2 is 90 degrees, pi is 180 degrees. You're in the second quadrant. So I set up a triangle in my second quadrant. Notice that for the second quadrant, the y values are positive and the x values are negative. That's going to be important. So we make our triangle. Notice that we have theta, the angle, coming from the origin, just like we always have for these constructions. And we can see that sine of theta is 4/9. And we know that sine is opposite of our hypotenuse. So here's our angle theta. Opposite is 4. Hypotenuse is 9, being across from the 90-degree angle. But we still need this missing leg, which we are going to find through Pythagorean's theorem. So, at first I called this x, just, let it be a variable. Leg squared plus 4 squared equals 9 squared. So x squared plus 4 squared equals 9 squared. Rearrange, solve for x. You find that that missing leg is the square root of 65. However, we're on the negative side of the x-axis. We're in quadrant 2, meaning that this leg, this adjacent leg to angle theta, has to be negative. Okay, if you don't have that negative there, you're gonna have some wrong signs in your calculation. All right, so we have our triangle figured out. and we want to calculate the tangent of 2 theta. And that means, if we look at our double angle formula for tangent, which is right there on your formula sheet, it's right here. If we look at that double angle formula, we're going to need to know tangent of theta. So if we come over to our triangle, the tangent of theta, and we know tangent is opposite over adjacent, well, opposite of theta is 4, adjacent to theta is negative square root of 65. So tangent of theta is 4 over negative square root of 65. So multiply top and bottom by square root of 65 to get the square root out of the denominator, and we get that the tangent of theta is negative 4 square root of 65 over 65. And now let's take this and plug it in for tangent theta in these two locations. All right, so applying the formula, 2 tangent theta divided by 1 minus tangent squared, so that's 2 times negative 4 root 65 over 65 divided by 1 minus negative 4 root 65 over 65 squared. Notice here, I show how you can make that calculation. That 1 minus this whole mess here in the red box is really equal to 49/65. Here's all the work to verify it. So now if we look at the numerator, 2 times this is going to give us negative 8 root 65 over 65. We know the denominator is going to give us 49 over 65, so I did keep, change, flip, meaning this gets flipped upside down. And notice that the 65s will cancel, leaving you with negative 8 root 65 over 49, which is our final answer. So, somewhat difficult calculation, but we know from this unit was filled with difficult calculations, especially when you consider tangent problems. So make sure you know how to do those. All right, last problem, number 15. We want to solve for the sine of alpha plus beta, the cosine of alpha minus beta, and tangent to alpha, given that the sine of alpha is negative 4/8 and that alpha is between pi and 3 pi over 2. So, and also that cosine of beta is 7/9, where beta is between 3 pi over 2 and 2 pi. So we have 2 different domain restrictions, meaning we're going to have 2 different triangles. So the first triangle is in quadrant 3, pi to 3 pi over 2. I'll call that the alpha triangle, is in quadrant 3. And the beta triangle is in quadrant 4, between 3 pi over 2 and 2 pi. So what I have here is those 2 different triangles set up. Now, I'm not going to sit here and break down the exact calculations like I did for the previous problem. You can see the calculations right here. It works the same way. You use the initial information to set up the triangle, and you use Pythagorean's theorem to find the missing leg. Just again, special consideration, make sure that you know that, in quadrant 3 over here, both legs are going to be negative because we're on the negative side of the x-axis and the negative side of the y-axis. Over here in this triangle, the beta triangle, this leg is negative because we're on the negative side of the y-axis, but this leg is positive because we're on the positive side of the x-axis. But once you have your triangles constructed, you're going to use those triangles to have the sine, cosine, and tangent of both triangles, which you can see labeled right here. And these are the values that we're going to use to make all of our calculations. So let's start with sine of alpha plus beta. Sine of alpha plus beta, if you look in your formula sheet, is sine alpha cosine beta plus cosine alpha sine beta. We have already done all these calculations. They're right up here. So sine alpha is negative 1/2. Cosine beta is 7/9. Cosine alpha, negative root 3 over 2. Sine beta, negative 4 root 2 over 9. Then it is just an algebra calculation. Negative 1/2 times 7/9, that's negative 7/18. Negative 3/2 times negative 4 root 2 over 9 is just 4 root 6 over 18. Common denominator, we can combine the numerators, and this would give us our final answer. All right, next, cosine alpha minus beta. From the formula sheet, cosine of alpha minus beta is cosine alpha cosine beta plus sine alpha sine beta. Again, from the triangles, we already have all the values that we could possibly need. We can see that cosine alpha is negative root 3 over 2, cosine beta 7/9, sine alpha negative 1/2, sine beta negative 4 root 2 over 9. Going through with those calculations, negative root 3 over 2 times 7/9 is negative 7 root 3 over 18. And negative 1/2 times negative 4 root 2 over 9 is going to be 4 root 2 over 18. giving us this is our final answer. Finally, we have another double angle tangent problem here for number 3. Here's our formula from the formula sheet. We already know that the tangent of alpha is root 3 over 3. So we just plug that in for tangent alpha in both of these locations. And then we calculate. So 2 times root 3 over 3, that's going to give us 2 root 3 over 3. In the denominator, root 3 over 3 squared is going to give you 3/9. And we have this 1, and we're doing 1 minus 3/9. And I'm going to go ahead and just replace this 1 with a 9 over 9, which we did right here. And that gives you the denominator as 6 over 9, which is just 2/3. Then at this point, we do keep, change, flip. 2 root 3 over 3 times, this thing gets flipped upside down, times 3/2. And notice these 2's will cancel, these 3's will cancel. All that's left is root 3, which is our answer. All right. So hopefully this served as a good review of trig identities. We can see not only double angle, sum, difference formulas, having to create triangles based off of domain restrictions. We can see all these problems on display. And we also had these simplifying and verification type problems. So even though it's only 5 problems, in my opinion, it does a pretty good job of showing you a lot of the skills that were on display there in Unit 6. Okay, have a